So thank you for having me. I'm really excited to be able to do this presentation at the American University of Cairo, especially more so that we've been collaborating a lot on this project. So let me briefly introduce myself. So my name is Johan Euphrosine, but online I go by Tropi. I joined Google in 2011. And I've been doing like the same job since then. I'm a developer relation engineer, meaning that I focus on improving the developer experience for products that target developer. So I worked on a variety of products like since I joined Google, ranging from cloud, Android, and IoT things. But I joined like this new team, like the hardware toolchain team, relatively recently, like 6 months ago, and with very little kind of background in hardware engineering. And so the idea was to look at this field with kind of software engineer kind of mindset and see how we can improve this experience. And that's the reason why I joined the team. So the wider mission of my team, of my parent team, is to accelerate Google. And the reason we need to accelerate Google is that the demand across Google is rising across like all fields. So we see more demand for search, we see more demand for cloud, we see more demand for YouTube. And we found out that like we couldn't really keep up with software optimization. So my team as Google, my parent team as Google work on like basically optimizing the workload that run on the server, making sure that the toolchain is optimized, making sure like the library are optimized so that you can extract like the very last performance out of each cycle. And we had like something that was great with like new generation of silicon and new generation of CPU, is that each of the new generation will give like an instant boost of performance. But as you see inside this curve, like it's getting less and less true. Like as we get more and more transistor inside those chip, like the performance gain that we gain for single thread performance is not following. And while there is still a lot of places where we can still optimize, like if we take a program that has been written in Python and you go all the way up to optimize it and optimize like the SIMD instruction of its processing, like you could get as much as like multiple 10,000 x performance. But what if you need to go beyond that? Like what the kind of flag that you can pass to GCC when you want to optimize further? And like that's the reason like we started working on accelerator. Like we found out that there is just so much that we can do in software, and that the kind of next barrier was for us to like write like custom processor that do exactly like one type of processing and accelerate like those workload further, so that like we can get like faster computation for a better power ratio. And so that's like what started with the TPU initiative at Google. And but we found out that like actually developing those like specific hardware, those accelerator cost a lot. Like it costs a lot in terms of design cost, it costs a lot in terms of verification cost, and it costs like as the number of transition increase, like the cost for those scale like exponentially. So that's like kind of what refined like our parenting mission into like what can we do to accelerate accelerator? Like what would we do to make those kind of accelerator like the TPU like faster, cheaper, and easier to develop. So and that's kind of the thought there, is that like we don't need to do like just like 10x more like accelerator. Like we're going to need accelerator not just for machine learning, but for a lot of things, for video encoding, for video transcoding, for like processing data, like for serialization, deserialization. There are going to be a lot of accelerator inside each of the workload that we want to accelerate. And if you compare like the current pool and the growth of hardware engineer, because we've seen that the cost of the labor cost like for developing those accelerator was increasing, you can see there is currently in the US like a pool of like 70,000 hardware engineer. It's growing by 6% each year. And you can see it's like almost like a 1 order of magnitude difference if you compare to software. And also like the growth also is like 5 times more. And so the kind of thought there was, and like if you look at the trend of like, for example, the simple Google search for computer science versus like electrical engineering, you see that like computer science is growing like fairly, and like the kind of interest inside electrical engineering like stays flat or even go down. And the interesting trend also is that like kind of the general topic of supply chain and semiconductor is trending up as well. So you can see that there is an interest inside the industry, inside the community in general, into the supply chain in the semiconductor that's rising, but we don't see like the same engagement inside the electrical engineering field. So the idea is very simple: is that like how, if we want to accelerate that growth, if we want to be able to develop more accelerator, like how can we turn like a fair amount of those software engineer into hardware engineer, or at least how can we make them like work better together? So that's kind of what my group inside this team is about. It's about like making custom silicon easier to build for everyone at scale, just like software. So that we can have like something like ultimately like the goal will be to have something like GCC-O silicon, where you can't optimize further in software, like you specify like the part of the processing that you want to do in hardware, and you will use GCC with that flag, and you will get like an accelerator that you can tape out. That's kind of the vision. But so I think it will be like nice to compare like the kind of software world and hardware world. Like if we want that vision to come true, at first we need to kind of look at both of those worlds and look how they differ. And so like in the software world, like computing is a community with very, very fast iteration cycle. Like when you work on a software project, you will like recompile almost like every minute or every 5 minutes if you're, depending on what kind of language that you're working on. You will have like unit tests that are running in the background constantly. You will get very, very tight feedback when you are developing. Like most of the API that you will manipulate will be open source. Like you will use API like POSIX, HTTP, REST. Like if you are doing some visual thing, you will use like OpenGL or Vulkan. And on top of those open source standard and open API, like the tools that you will be using, like your compiler, your development environment, like your debugger, most of those are open source. And like the tools that are like mainstream inside industry are tools that you can like readily install on any machine, any OS, and where you can really get started really easily. And the other kind of interesting thing inside the software world is that like there is a lot of software reuse, like kind of reusing a library to do some processing is kind of the default. Like what you end up doing a lot of the time is taking a lot of different library and like gluing them together to do what you want. And if you compare that on the silicon world, like the hurdle is like way higher. Like the feedback loop could take days or even weeks sometimes. Like the very bottom of the specification of the API that you need to interact with, like the PDK that describe a process, describe like what kind of cells are available for manufacturing, like your chip, and building your logic. This is under NDA, so meaning most of the time. So meaning that you, before even trying or thinking of developing or studying this API to know what you want to do. So I see a message that the screen sharing is not working. Can you confirm if that's the case? Because do you see my screen?
It's fine on my side.
Okay, cool. So yeah, I was saying that the very bottom of the layer is like under NDA, which cause people like they can't even like study the technology before adopting it. Unless they start like signing some contract. Most of the tooling that you manipulate there is proprietary. Like you often have to pay a license or negotiate a license with your university or the company or the institution that you work with in order to be able to start developing. And like there is and because like there is really an alignment between the process that you are targeting, the PDK that you need to use for that process and the proprietary tool that you will be using, there is very low IP reuse. Like people have to have the same combination of tool like PDK and like actual like foundry that they target for them to be able to share a design with you. So meaning that it's not really easy to port like a design from a tool from another or from a process from another, which causes a lot of people to re-implement things by default, and often like those tools will also come with those IP blocks that are tied to it. And so that's kind of where we started, like between this dichotomy between software and hardware, and trying to think of what we could do to close the gap between the two. And so we thought that in addition, in addition to have like advanced PDK under NDA, we also needed like some open source PDK. And like we thought like instead of only requiring like proprietary tool, that we thought that like having open source tool, silicon toolchain option will be also can people help like adopting that field and get more familiar with it. Instead of like having a very few IP block to be able to reuse by default, like having a large pool of open source IP that you can draw from could also allow and empower the capability of people to build bigger things based on common and shared like building block. And we know also to get like a faster and cheaper like manufacturing option, so that like people could like get a quick feedback on their design and iterate, because like when people get started, they do a lot of error. And so the idea is that like if you reduce like the cost of making those error, and if you both in time and money, you allow people to make progress faster. And so all those kind of needs were captured originally in a paper that was submitted 2 years ago at ICAD by some of our team member or our team founder. And you have a link there if you want to look at that paper. It's called The Missing Pieces of Open Design Enablement. So the conclusion that basically if you get an open source PDK, an open source toolchain, and some open source IP block and fast iteration cycle, that's where you can get like an open source silicon ecosystem. So that's what we like started to kind of work on as a team. And so we started working on those three things, like first release an open source PDK, found an open source silicon toolchain, and then sponsor like a silicon realization program. So that like the missing pieces that we identified in the previous slide are kind of filled, and that we can get like this ecosystem. So I'm going to start with the first one, like the open source PDK. So 2 years ago, a little bit more than 2 years ago, we announced like a partnership with Skywater, and we managed to convince them to open source like their 130 nanometer PDK. That's actually manufacturable, like a PDK that they use commercially within their foundry. So we managed to convince them to release it in an open source license without any NDA to sign. And the only thing that you need to do in order to access this PDK is basically git clone. It's already readily on GitHub. You can just git clone it and access it. And the license is APH2, which is a filing license that should allow to reuse it in a variety of open source projects, and also proprietary project as well. And that's what the process looks like. So it's a fairly mature process. It was, I think, originally a memory process that was came from a long series of acquisition of foundry and ended up in Skywater. Like there is like a 5 metal layer and 1 metal interconnect, and there is like a library of standard cell. There are also like some flash Sonos cell as well, and also like I think that's really interesting inside of it is that like there is a cell for advanced technology like ReRAM. The more important thing about that PDK, beside the fact that it's open source, is that it's manufacturable. So it's possible to like get that PDK, do a design with it, and contract with Skywater to get like some real chip manufactured about it. So it's not just a PDK for research; it's a fully manufacturable PDK. And so after we release that PDK, we've seen a growing engagement from the community. Here you see in green like the kind of from the moment of we release the PDK, the number of stars that we got on that repo, we kind of went over really quickly, and like kind of reached the level of some projects that have been there for a long time. And we also have a community. So that has more than like 3,000 member now, and you can join it like with that domain. Like there is also the join dot. There is also open dash source dash silicon dash dev that's pointing to the same community. And so like that was like the first thing that we did, like to provide like an open source foundation where we can like people can build their design. But like you can't really design anything in the open if you don't also have like an open source toolchain. And so that's like where we started some academic collaboration with a variety of universities to have like a project like Open Road or Open Lane being funded with a fair amount actually of the Open Lane developer or even like a majority of them like actually located here in Egypt. And a lot of them are alumni of the American University of Cairo. And we also like worked with other university to have like IP block generator. So like one of them is OpenRAM, another of them which is like in direct collaboration with the University of Cairo, American University of Cairo is DFFRAM. We also collaborated with the University of Michigan to have like an analog block generator called OpenFSOC, and also with the University of Berkeley. And Google also has like their own open source project within that space. So we started like working on a high-level synthesis language called XLS. We have like some system Verilog tooling for indexing and linting that's called Variable that started at Google and then like is now maintained inside the Chip Alliance. We have like a RISC-V ML accelerator SDK called CFU Playground that allow you to work and customize a RISC-V core with specific instruction. There is a team at Google that's working on a layout generator called GDS Factory that's used for photonics, but could also be like reused for CMOS process. And project like Open Titan also get a lot of contribution from Google and like are now owned by an independent organization called Low Risk. So that was like for funding like open source toolchain, the open source IP block. And then like now that you have the PDK, you have like the open source PDK, you have the open source tool, so you can get started with your design. But it still costs a lot of time and money to manufacture real chip out of it. So we also wanted to do something about that. And so what we started to do is that we identified that there is an opportunity here to sponsor a silicon realization program. So we started like the Open MPW shuttle program for this PDK, so for the Skywalker 130 PDK. So the idea is that like this shuttle program is managed by a company called Efabless that has an expertise on like shipping design to foundry, getting them manufactured and redeliver them to the client. The project itself will be funded by Google, meaning that Google will pay for the mask manufacturing cost and for the cost of the wafer, and the actual like wafer will get manufactured by Skywalker. So it's like a partnership between three companies to have like an MPW shuttle program that anybody could join. And so the rule of the program are really simple. Like there is no cost for the people who enroll in this program. Like the only requirement is for your design to be open source and to be reproducible with the open source tools. There is one feedback every 2 months, and like you should get like back your chip like in around like 6 months time. And now 40 projects that are selected. So and currently it's selected by lottery. Out of all the design, we look at them and we select like random, 40 random out of them. And there is also like a kind of idea to make the process selection a little bit more fair. So I think inside the last shuttle, they also give an advantage if you submit your design earlier. And the shuttle program is run like by a company called Efabless. And so they also have like another program called Chip Ignite that's basically has very similar characteristic as the shuttle program that I just described, unless that you can have like proprietary design on it. Your design doesn't have to be done with the open source tool and it doesn't have to be open itself. And this program is commercial, meaning that you can still target the open source PDK, but you can pay money to get like more chips and to produce like small volume. And so for this silicon realization program, we run the first run in November 20. We ran the second run in mid 2021, and we had like multiple more in 2021, and we are I think to like the third one that we just announced in 2022. And we've seen like a growing engagement across like all those shuttle runs. So so far we run like 6 of them, and we accumulate the pool of like 350 or so design that were submitted to this project. And so here you can see like in clear you have the number of design that got submitted to each project. And you can see like the total pool of design that was submitted since the beginning of the program that can grow nicely. And we also saw like a variety of engagement for various countries. It's not just the United States. It's not just that's submitting some design. We've seen like design submitted, of course, from Egypt, like from Japan, and from like a lot of different like countries. And like the interesting thing is that like the like more than half of the people that we surveyed that enter like this program were declaring themselves as first-time designers or coming from a software engineering background. And so that's, I think, interesting because like it kind of fulfill or kind of start to map nicely inside the vision that we had at the beginning of the talk, which is like to try to find a way to make those this large pool of software engineers like more familiar with chip manufacturing. And so I'd like to highlight a few projects that were kind of submitted to this program. Like the first one, like was that I think is really interesting, was OpenFSOC, which is an analog ledger generator. So they managed to like have like some automated flow for analog generation, where they were able to generate like temperature sensor block, LDO block, PL block with different characteristic. And the interesting thing that they explore here is portability between processes. So they send like this process, this like design to the Skywater 130 OpenMPW program, but they also like sent similar block generated to a global foundry tapeout that was targeting a totally different node, like a 12 nanometer node. And so to kind of show that their tool enable portability between multiple technology. So another like a very ambitious design that we saw is like Microwatt, which is an open power SoC that's 64-bit, has a FPU and is Linux capable. I think it's like out of all the design that we saw, it's like one of the most challenging and more complex one. And another like interesting like type of submission that we've seen is like group submission. So there is like this class online called the 0 to ASICs course. They kind of started quickly after like we announced this program. And what they are doing on that class is that they use like a single like project area, like the place where you usually have to fit your design when you want to submit something to the shuttle. But instead of putting like a single design inside of it, they put like 16 of them. And so that allows like people to share their experiences and to work together and to share like some of the burden of hardening like the design. And that allows them to get started with the course material and to do like a first step out with like people that can help them that are riding the same shuttle and people that are like actually working together to like a single submission. And so I actually enrolled that course and was able to submit a design to it. So I will like actively recommend it as if you want to get started with this and you are new to the field like me. And we also saw like a fair amount of submission from Egypt. Like I think we've seen like a submission from Egypt on almost like every shuttle, with things ranging from RISC-V SoC to analog block like PLL or IDO, but also like some test structure for the GFFRAM project that also like developed inside the American University in Cairo. But it was not like only success. Like there was also some issue with like this program. Like we had actually like some violation as part of the the test harness that's around like the design, and we found out that, or we thought at least that most of the design from the first shuttle will not be able to function because of this violation. But what's interesting is that like that's actually because like all the bits were open and people like could study and reproduce like those design, and like were really involved into like the tooling and the PDK and all the activities that was around it. Like some people inside the community actually try to find out a way to make those chip works. And so they managed like to tune like the voltage supply of those chip like very carefully with an FPGA board that they attached to a test board, and they managed to get those design working by slowly like controlling the voltage that we are feeding to them. And so I think that's like a good example of how when you give power, when you give people like the tools and the power to own their own tools, to own their own process, to own their own flow, they are able to kind of, they're never blocked by any problem. And they can always try to find a solution to unblock things. And like, yeah, here you can see like one of the people from the community who actually posted like some of the example that they had working with this test board, and you know, like that person has a clock on their desk that's running like one of their design with some manufactured silicon that were manufactured using an open source PDK, using an open source tool, and like reusing like open source design blocks. And so, and I think that we were also able to do after getting those first chips is that we were able to do like imaging of them and try to inspect like the structure and inspect how they were like how the silicon was actually coming out, and like verify things like if like the actual manufacturer things were corresponding to the public documentation we had like inside like the PDK. And so, and we also recently announced like also a set of measurements that were done using this first chip, and where we can like get those measurements, we could potentially also improve like the simulation model that are inside the PDK. So there is a lot of good things that happen when we have things, all the elements of that flow that are open from top to bottom, because like what you get at the end of the process, the wafer is also a thing to make like the bottom stack, like the PDK better. And toward that, like that goal, we announced like a partnership also with NIST, where we are gonna get them to test, basically characterize the same test structure that I mentioned before, in order to get like some new data across a variety of temperature conditions, so not just room temperature condition, but also like extremely cold temperature and extremely hot temperature, and like get potentially new data there that could be used, like as I was mentioning earlier, to improve like the simulation model that we have for this PDK. So that's like the three things that Google is trying to do to help, like trying to release open source PDK, funding like open source silicon toolchain, and sponsoring this open silicon validation program. And the goal is that with this we can get like an open source ecosystem, like with those three things, like the PDK, the tool, the design, and the thing that makes everything spin in the middle, which is like the MPW program. So the idea is that like how do we grow from there? Like so if we get more PDK, that's also one way that we can develop that program further. Is like it allows us to get better design, because like those design will have to be ported across different PDK, and they would have to become like less specific to one, and they will become like more portable and more generic. It also allows us, if we release more PDK, to release to have better tool, because the tool will get less skewed toward like this one open source PDK we have, like the Skywater one, and will be able to adapt to reuse a variety of process and a variety of characteristics of that process. And that can also allow us to have more shuttle, because that's usually how we work when we when we negotiate a partnership with, and we try to find funding to open source a new PDK. We also negotiate the funding for running shuttle run for that PDK, because it's we can't make the PDK better or make the tool better if we don't actually manufacture chip out of it. The work of the tool, like more work or more investment on the tool, can also help. Like if we make the tool better, like the design will get better as well. Like they will be able to achieve like better performance. They will be able to achieve like a better like power consumption or fit in a more optimized area. It also allows us to like make those tools like I was mentioning before, like more portable across different technology, and like it also directly impacts like the user experience of this new designer. Like if the tools are better, like if they are not crashing anymore, or if they are well packaged, and if they are easy to install, if there is documentation to that explain how to get started with them, that directly also affect like the adoption of people that are coming and try to adapt those tools. And the last thing that we need in order to grow that program is more design. Like, because if we have more design, they will push like the boundary and the limit of the tool further. So we'll be able to find new issue inside this tool and make them better. We'll also find like the issue inside those PDK and find like that there are things that are missing or things that will be improved. And like if we have more design and we can justify also like funding more shuttle, if we are over capacity, we can try to find more funding to organize more shuttle if we see that all the shuttle are crowded. But next to that open source silicon ecosystem that I described, there is also a proprietary silicon ecosystem that we shouldn't ignore. And like those two ecosystems are really next to each other. They are not, I don't think we should say that they are competing. I think that they should really fed from each other. One example that we can have like those kind of ecosystem coexist and collaborate is that like we could use like those open source PDK with the proprietary tools, but we could also like use those more advanced like PDK that are under NDA and not open source with open source tools. The other aspect is that like those open IP that people develop open source IP that people develop could also be retargeted, like the OpenFSR project has shown to target like more advanced node, but also like we could and hope that people take their closed source IP and port it to use like the open source PDK. And more generally, like if we increase the number of collaboration, like I just suggested between those two communities, there will be more people coming from the community and going to the industry, and there will be more people like coming from the industry, like feeding knowledge inside that community. And so you can imagine, and that's kind of the ideal path for someone that gets started inside this ecosystem, is that they start like within the open source ecosystem community. They start with a group submission, maybe with some of the course like the ASICs one. Then they graduate into like submitting their own shuttle entry with their own design. And then like maybe they contract with the fabless in order to get like more volume manufactured and get more chips. And like maybe they grow their business and they end up like needing to manufacture like a full wafer and contract directly with SkyWater. And like when they're at that point, they're really part of the industry. They're really like a fabless company, like that's manufacturing like silicon. And that's kind of the path that we want to enable, like of like people flowing from this open source community to join like the industry. And so we've got like a few announcements in 2002. We managed to onboard a new foundry. So a global foundry has joined the program and open source like their 180 nanometer PDK. And so you can like look at the link there and you will see like the documentation for that PDK. There is also like we also announced that later this year we'll work with SkyWater to open source a more advanced PDK, a 19 nanometer PDK. And like also I wanted to kind of quickly mention like some project I'm working directly on is like inside the ecosystem. So I'm working on packaging like a lot of those tools and those PDK using a packaging system called Conda. I'm also working on creating notebooks, which are like a potential document that allow you to get started with those tools directly inside your browser. And I'm also like working on making sure that those tools can work at scale on Google Cloud Platform with a solution that you can deploy to your project to do like parameter extraction. So that's a small showcase of like a recent experiment I did where I took like the open source silicon to chain flow done by OpenLane for the RISC-V core and run like 10,000 experiments to explore the best ratio between area and density and to see and try to optimize power. So here you can see like all the experiment that we run, like the power measurements and all the chips that got generated. And so yeah, that's my last slide. So I hope we didn't went too much over. So I encourage you to join that community. So there is like the Slack community, open source-silicon.dev. There is also a web portal that we created on developers.google.com/silicon, where you have pointer to all of those resources that I just described. And there is a more generic blog post that we ran like back in June that explains kind of the motivation between this for this program. And so I think that's it. Thanks for having me, and I hope you enjoy.